Alright, this is going to be a long one. Alright, so start by considering this matrix and find the inverse matrix using this method. So what we're going to do is we're going to take this matrix, augment it with the identity matrix, and perform Gaussian elimination until we've achieved the identity matrix on this side, which will give us our inverse matrix right here. So that's it there, and that's the checking online to make sure it's right. Alright, find the intersection points of these lines. I'm going to use a different parameter in the second one. I'm going to call it Q. I got parametric equations for this line, parametric equations for that line. I'm going to get all my variables on one side and have it over here. Then I'm going to plug that into a matrix and augment it with my real number solutions over here. And I just employ Gaussian elimination again. Find out that I got an inconsistent system, which means the lines don't intersect. Alright, consider the matrix A. To find a basis for column A, I'm going to put A in here, reduce it down, and find that I've got pivots in these rows. And those pivots indicate the column vectors here that form the column space. Alright, so it's going to be the span of these three vectors. So any linear combination of that is going to be in the column space of A. For row space of A, you want to continue on, since we're using the same matrix. You got to get this all the way down, so use Gauss-Jordan. You want zeros below your pivots, above and below your pivots rather. And so you go ahead and do that, and you've got it reduced here. And the ones that have pivots, you're just going to copy those rows down, and you're going to have this as your row space. And to find the null space of A, we're going to take that same reduced matrix that we have, whatever one have it. Then what you're going to do is you're going to set up these variables and solve for them. So we're going to have two parameters, two free variables. So x4 is t in this case, and x3 is q in this case. Go ahead and solve it, and then set it up like this. And these vectors here, the ones that are being multiplied by the parameter, are going to be your null space of A. Notice there's 2 here, and there's 3 here. The column space plus the null space, the number of vectors is going to be the number of columns in your matrix. So this linear function, we want to find the standard matrix representation for this. So what you do is you just plug in, well, you're going to use the identity matrix to solve this. So we're going to take the first column of the identity matrix, plug it into here, solve, get a value, put the other column, the second column in there. So there's I hat and that's J hat. Go ahead and that'll form our matrix. And so basically, if you multiply this by any old vector, 2D vector, you're going to apply that linear transformation here. All right, so find the standard matrix representation for the linear transformation. L goes from R2 to R2 that projects the vectors onto this line. So for that line, we need a direction vector. So I just picked a nice set of points, and I got my direction vector. Now you're going to project all of the, well, it's 2, so you're going to project these 2 vectors onto that direction vector, and that will form the columns of your standard matrix. Pretty straightforward. Find, oh, yeah, this is wrong. Find the standard matrix representation for the linear transformation. You're going to apply this to this. You just multiply these 2 together. Whatever your result is going to be that. I did that wrong the first time. I didn't actually update it. Alright, so shorter answers. We're going to do some complex number arithmetic here. So we've got z equals minus 5 minus 3i, and w equals minus 4 minus I. And we want these different results in the form of a plus bi. So 2 times the complex conjugate of w minus z plus 5i. So just remember the complex conjugate, you're going to flip this sign on the imaginary part. And so you go ahead and multiply this out. You're going to get this answer. The magnitude of 3z minus w, well, you just plug those guys in. And then once you get everything reduced down, you just take the magnitude of that, you square the components, and take the square root, and that'll form your answer. It's going to be a real number. W times the conjugate of z. So again, z was minus 5 minus 3i. So this is the complex conjugate. We get this result. And w divided by z, well, you take w divided by z, but you've got to multiply this by the complex conjugate of z. You'll notice that w times the complex conjugate of z is this guy right here. So I already have that. And then you go ahead and multiply this out. You're going to get 25 plus 9, because remember, this I is the square root of minus 1. And if you want an a plus bi form, there you go. Find all the fifth roots of negative 16i. Write them down in the form of a plus ib, where a and b are real numbers. Plot your answers on the complex plane. So what we're going to do is we're going to take z. We want to find the magnitude of that. That's going to form the radius, because we want r and theta. So negative 16i. I got to draw this right quick. If I'm going on the complex plane, negative 16i sits down here. So that'd be theta, and this would the length of this is r. So just take the modulus of this, and you're going to get the radius of that vector, or the length of that vector rather, and you're going to get theta. I just computed the fifth root of 16 on a calculator just to get that, but you're not going to have that in the exam, so just leave it as that if you can't solve for it easily. So this is the general formula. Z equals r times cosine theta plus I sine theta. And then you're going to get the radius, which we solved for, was 16. Cosine theta, where theta is 3 pi over 2. And then we're going to go ahead and compute the fifth roots of z, so it's just going to be that, the fifth root of 16. Since we're taking the roots, you divide this by 5, but remember, this is there's going to be a bunch of solutions to this, but essentially when you take the fifth root, you're going to take that vector. It's going to be that long, this long, right? It's shorter than 16, and you're going to divide the plane radially into 5 pieces. So you're going to have 5 solutions. So I just add 2 pi k, where k is an integer. I'm just going to choose these values of k, and then I'm just going to compute my new angle each time. Some of these can be reduced down, but that's okay, not a big deal. And then ultimately we're going to get things in. You're going to get things in this form. If you write that, that's technically all you need. But and when you graph it, it's going to look like this. Which, remember, it was originally starting here, so this is the point at which you're going to divide everything by that. You'll notice that the distance between these two is just kind of the change in theta as you increase k. You can decrease k, and just remember it goes the other way. Otherwise, it's going to go counterclockwise, like normal. Okay, so decide if v is in the span of those. In other words, is v a linear combination of these three? Well, how can we find out? We're just going to take these to form a matrix and augment it with v. And if it is a linear combination, we'll get a consistent system. Boom. That is inconsistent. 0 is not equal to minus 7, so v is not in the span. Alright, keep going. So, decide if this set is independent. Well, if it's independent, you put it in a matrix, reduce it down, and if you have no parameters, or you got a pivot in every row or column or whatever, if this reduces nicely, then you'll get a... if it were to reduce nicely, it'd be independent, but this one's not, so it's a dependent system. Anyway, that's pretty straightforward. This one is going to be just some matrix arithmetic. So we've got A, B, C, and R. 7 times A, so that's a scalar, so you distribute that 7 minus R. So because these are the same size, i.e. they have the same number of rows and columns, you can do addition and subtraction. So you just you do each component one at a time. So you're going to have 7. Once you distribute the 7, you're going to have, let's see, I probably should have used a tripod, but that's okay. You're going to take 7, and you're going to add, or you're going to subtract, negative 7, you're going to subtract 2 from it. So you just do it component by component. That's how you get that. A times C you employ your regular multiplication. Just make sure I always do this. If these two numbers are the same, i.e. your columns of your leftmost matrix equal the rows of your rightmost matrix, then it's possible to do that. And then the result is going to be this size matrix, a 2 by 3. So you go ahead and, well, it's going to be negative 1 times 11 minus 2 times negative 1. So that's going to be that. Oh, did I make a mistake? Negative 11. Was that a negative 1 normally? I guess I made a mistake. Because that would be minus 2, which would be plus 2. So anyway, whatever. It's all good. Just, that's going to happen. 3 times C transpose. Well, if that's C transpose, you just take these column vectors and they become your rows like this. And 3 is just a scalar, so you can distribute it that way. You can get that done. B times C can't be done because B is a 2 by 1 and C is a 2 by 3. So a 2 by 1 and a 2 by 3. So 1 and 2, it can't be done. B times B transpose, you get a 2 by 1 and a 1 by 2. Oh, I've written there. Anyway, so you go ahead and multiply those out and you'll get that. Remember, your result's going to be a 2 by 2. So just know that. Then if it confuses you at all to multiply these out, well, just remember this is the result you need to go for, and you can't mess it up. Alright, so same thing, B transpose, except, well, not the same thing, because it's not commutative. Obviously, we get a different result. We're going to have a 1 by 1 matrix here. 58. Done. Alright, so find e to the 2 minus I in the form of a plus bi, where a and b are real numbers. So the generic formula is going to be r times e to the I theta. And then what you're going to do is, r in this case is 1. And theta is going to be negative 1. Oh, well, I guess if I do it this way, then that works. Yeah, theta, well, this is e squared divided by e to the I, so yeah, if I'm treating it like this, then theta in this case is 1. Anyway, so well, we're dividing by a complex number, so you better multiply by the complex conjugate. Then you'll find out that you get cosine squared plus sine squared, and that's going to be 1. And then e squared was up top, so you're going to multiply that by that. There's your a plus bi form. Okay, let M be a 2 by 4 matrix with entries labeled as if Mij, where I is the column index, and J is I is the row index, and J is the column index. So what you're going to have, well, just like this. I just write it out like this, just so you know what the hell's going on. And then you just apply that equation, solve for those values, get that. State the basis theorem. Let S be a subspace of Rn. Then any two bases for S have the same number of vectors. That's one of the several theorems we got to memorize for this thing. State the definition for a set of vectors S to be a subspace. So S can't be empty, so it has to contain a vector. If X is an S and Y is an S, then X plus Y is an S. So, for example, if we've got two different vectors in S, their linear combinations need to be in S as well. And if if alpha is in basically complex numbers and lower, so you're not talking about quaternions and stuff, you're just basically complex numbers and real numbers. X is in S. Oh, sorry, and X is in S, then if you take a scalar and multiply it by X, that is also found in the subspace. Yeah, S is non-empty, etc. This is just me putting it in my own words. Find an elementary matrix that corresponds to the elementary row operation. Is that what I did? Oh, right. Yeah, okay. Yeah, so you would just, whatever you did to this to make it happen, you took 1/2 row 2 plus row 3, because that would be, or sorry, negative 1/2, right? So negative 1 and 3, that becomes 3, and then you add those to the bottom row. You're going to get that. So that can be represented by multiplying. So you just apply that transformation to your identity matrix, and you get this matrix on the other side. That is the elementary matrix. All right, so write down the inverse of this matrix. I just augment it with the identity and solve for it. Okay, so that was the midterm number 2. We're 15 minutes in. All right, so this was, well, we're just doing some complex valued functions. So in this case, cosine of z, the generic formula for the cosine of a complex number is e raised to negative I times that complex number plus e raised to the power of I times that complex number. So in this case, we had z equals this, so we go ahead and plug that in, and you just distribute that I and up there. You can separate these exponents into their real and imaginary parts. The imaginary parts can be represented in polar form like this, because otherwise it would be e to the negative 3i would be the polar exponential form. So the angle for this one is negative 3 radians, and then this one is 3 radians. So it looks something like this. And then if you remember a little trig trick, you can say, well, the cosine of negative 3 radians is the same value as cosine of 3 radians. So we're able to put 3 in here because we're just looking to factor out the cosine, so we can get like in the form of a plus bi, because this is a real number and this is an imaginary number. And then remember that the sine of the negative 3 radians is the same as negative sine of 3 radians, and then we can factor out this sine 3, so you get this guy. Exponential functions, they're going to be in the form of e raised to the z equals e to the x, which is e raised to the real component times, well, this. I is the angle we're dealing with is pi over 4, so you can convert it into this guy. So pi over 4 in this case is y. So you go ahead and write it like this. And if you wanted, because we had a nice angle, we can go ahead and call cosine of pi over 4 what it is, which is root 2 over 2. And this is your a plus bi form. All right, so sine, define the sine of an angle. Very similar to this, except you're going to be dividing by 2i, and then you're going to be subtracting this one from this one. So if it looks like this, it's going to be minus e to the negative iz plus e to the iz divided by 2i. That's the difference between the two formulas. So there's this guy. And then our complex number here, we just plug it in, distribute the I, separate the real and imaginary parts, convert the imaginary parts to polar form. Remember our little trick we did before with trigonometry. Factor out the sines and the cosines. I believe that's the right answer because we're dividing by 2i. So in this case, sine is the real part. So this is going to be the sine of that complex number. Anyway, that's cool. So, and for logs, log of z, so log base 10 of z, I guess, and then is ln of the magnitude of z, so that'd be 3 squared plus 4 squared, all square rooted, which is 5, times I times the argument of z. The only thing you got to know is that the argument of z is theta, which is the angle from the positive x-axis. So just pay attention which quadrant you're in. You may have to subtract the tan of that angle from pi or 2 pi or what have you, just to make it make any sense. And you add plus I 2 pi k, where k is an integer. That's going to be how you do those. So those are the complex number functions, or complex functions, exponential and trigonometric. All right, so workshops. Workshop 10, orthonormalize this set. Well, first thing what you do is make sure that their dot product isn't 0 already, because that'll save you some time. So in this case, 1 times 3 plus 2 times 4, well, that's not 0. So if you want to, you just pick a vector that you want to leave alone, and then you can make the other guy a normal to him. So what you can do is v prime, I'm going to call it, is going to be the vector that is going to be normal to u. I should write u prime. I do this later in this notation, but anyway. So v prime equals v minus the projection of v onto u. So you're going to write v minus the projection equals this guy, and then this and this form your orthogonal set. And if you want your orthonormal set, you're just going to divide by the magnitude of each vector individually. And then these guys they're normal, and they're also length 1. So that's cool. Orthonormalize this set. Again, do the dot products, find out what is normal to what. In this case, we're going to leave v1 alone. We're going to calculate v2 prime. So we're going to choose to make, this is after deciding that the dot products aren't 0 for these guys, right? Yeah, okay. So v1 we're going to leave alone. v2 prime is going to be v2 minus the projection of the original v2 onto v1 prime. And that's going to give us this guy. You just keep doing your reductions down. You get something like this, and you can just make it whatever length you want, as long as it's pointing, or that it's pointing in some direction, right? It's pointing in a direction that's going to be normal to this, right? So I don't care that it's pointing negative and that all the components are 2/3. You can just make it 1, 1, 1 if they're all the same. So that's v2 prime. Now, well, v3 prime is going to be v3 minus the projection of v3 prime onto v2 prime, and v3 prime onto v1 prime, or v1 in this case. So that's going to be this guy. You get that. You can rewrite it like this. So those will form your orthogonal set, and again the orthonormal set is going to be you divide by the magnitude of each vector individually, and then that'll form your orthonormal set. And find the orthonormal basis for S. So S is this subspace here. I noticed that v2 and v3, when I dotted them together, were 0. So v2 equals v2 prime, and v3 equals v3 prime. So all we got to do is get v1 going. So v1 minus the projection onto him, and then minus the projection onto him. That's going to give us this, which also gives us... Oh, wait. Yeah, when you add these all up, you get the 0 vector. So he's not included in the orthogonal set in this case. I mean, I guess he's technically in there because all the sets, I think, have to include the 0 vector. I could be wrong on that, but that's what you do in this case. And then the orthonormal set, again, you just divide by the magnitude of each vector and you're good. 4. Find the matrix representation of the linear transformation from R4 into R4, which projects each vector onto S. So S was this subspace. So we want to find the matrix that will, when you multiply by any 4D vector, will project that vector onto this subspace. I'm just going to use S. I'm going to use the regular lengths of them. I don't need to use this one. I think that's the case. So you take T of the first column of your identity matrix. I'm just going through all the columns. I'm projecting them onto this guy, and then I'm projecting it onto this guy. So this is like this many x. You go over this many x's, and then up this many y's. You're adding these two vectors together to get this, right? So you get these. They all have a common factor of 1/7, and you can represent your linear transformation as this matrix here. So that's cool. Fine. Okay, so workshop 9, this is eigenvalues and eigenvectors. So we're going to find both the characteristic polynomial, which is something that looks like that, and its roots. So you're going to solve for lambda. So you're looking for the eigenvalues for each of these following matrices. So we got this matrix. There's a formula. A minus lambda I equals 0. The determinant of A minus lambda I equals 0. So take the determinant of A minus lambda I. That's going to be this. You get that determinant. So you're going to negative lambda times negative lambda minus 1. So you get lambda squared minus 1. Solve for the roots of this guy. In this case, it's pretty damn easy. Get those roots. B, we're going to do the same thing. B minus lambda I. I'll take the determinant of that. You get our characteristic polynomial once you do some simplifying. And, well, there's your characteristic polynomial. If you want to find the roots, in this case, I had to use the quadratic formula to do that. And you get these god-awful looking things. C, same recipe. So C minus lambda I. Solve for this. Get your characteristic polynomial. You're going to solve for lambda. In this case, I used the quadratic formula, and I got me some imaginary roots. So this is going to be, remember, I is the square root of minus 1, so this is all good. So you get some imaginary roots in that case, but we can still use them. Find the eigenvalues, which was already done. So the eigenvalues that I found, and the eigenvectors for each of the following matrices. So it's just matrix A, B, and C again. So at lambda equals minus 1, which is one of the eigenvalues for this guy when we found it up here, we're going to take A minus lambda I, but lambda in this case is minus 1, so we're just going to, basically we're adding 1 to the downward column like this, the diagonal column like that. So you augment that with zeros, and you solve for your parameters in this case, and you get an eigenvector in this form. And I'm just going to plug in t equals 1. And so at lambda equals minus 1, this is an eigenvector. The eigenvectors are in this form. Okay, and so okay, yeah, lambda equals 1. So again, it's A minus lambda I, right? So we get minus 1 here down the diagonal. Augment it with zeros. You can always reduce this down. I believe he said that, something like that. So sometimes you can just go straight to that, put zeros down there, not worry about it. X2 and X1 happen to equal the same thing in this case, so we can just use 1, 1 as our eigenvector with an eigenvalue of 1. So that's basically, it's a vector pointing in a certain direction, and when you apply this linear transformation, the length of that vector is scaled by this eigenvector. So this one, it points it in the opposite direction, but this one, well, no, it points it in that direction and then reduces its size. It just makes it negative the length it was before, which I guess turns that around as well. But anyway, so this one, it doesn't change the length of it, but it points it to this direction. Anyway, I digress. So here's the other one that had the gross looking roots. You plug it into there, and you just see this, and then you just put zeros down. It's cool. Don't worry about it. I'm not going to figure that out. Just put zeros there, because that's what he said was fine, and it works. So, I'm solving for x1 in this case. I said x2 is the t, so I solve for x1. It's this guy. So x1 equals that times t, and x2 equals t. So at t equals 3 plus the square root of 33, you get an eigenvector in this form. And this is your eigenvalue. Same thing goes with this one. Subtract this guy from your, it's a minus lambda I, right? So keep going, put zeros. X2 is your free variable. X1 is this bad boy. Plug in strategic values of t just to make it look good. And you get this eigenvector, and then there's the imaginary one. So the imaginary one, the only real trick to this one over the others, just remember that 1 over I is the same thing as negative I. So you can go ahead and write it like this. Yeah, and then so that's an eigenvector. And then the other one is this one, right? So it was t divided by negative I, which is the same thing as multiplying by I. So that's cool. We'll do that. Find the eigenvalues and corresponding eigenvectors for each of the following matrices. So just keep going. Do the same thing. In this case, we got a 3 by 3 determinant to compute. I decided to use Laplace expansion to do this as opposed to Gaussian elimination. So the only thing you need to remember is this little checkerboard pattern once you've got your matrix that you need to take the determinant of. So yeah, it's similar to like how you do a cross product in engineering notation. Just treat it like that, plus minus plus kind of thing. So now we get this characteristic. Oh, that's our characteristic polynomial, and these are our eigenvalues for that. And it wanted to find the eigenvectors, so I circled those in green. So you just plug in your eigenvalues into this guy, and then you solve for your variables. So yeah, we only have one parameter here, so there's one eigenvector, and then here's the other eigenvalue. We go ahead, same thing as before. You know, you're subtracting lambda I, so just don't get confused with the negative signs. Keep going. We've got one free parameter, which is going to be x2, and it's going to be in this form. So it's pretty much just rinse and repeat. Anything special about this one? Not really. Same, just one parameter. Okay, here's another one. Do the determinant. Use Laplace expansion to solve your determinants in this case. So you're going to get this characteristic polynomial with these eigenvalues. Use those eigenvalues. In this case, we had two. X1 and X3 were parameters. So in this case, our eigenvectors for this eigenvalue we're going to have two for the price of one. This one, is it the same thing? No, this one only had one parameter. So you may get more than one. So if you see two parameters, don't freak out and don't combine them into the same vector. Just treat them like separate ones. All right, so that's it. Diagonalization. Here's an example. You have to have a symmetric matrix, okay? What do I mean by that? See those threes, see those fours, see those twos, see those zeros. Take the transpose of that and tell me what you get. You get the same thing. So that's a symmetric matrix. Determinant of that minus lambda I. Just do what we did up here, right? Same thing. Get your eigenvalues. Boom, I got three of them. So find your eigenvectors. Okay, well, so once we found our eigenvectors, you keep going, right? You got our eigenvectors for, okay, there we go. So here are our eigenvectors.